Yes, class. Am I audible?
Yes, ma'am.
Donna, Reem, Rifat, Sarah. Okay. C class. In the last Sarah, you had attended the last class, no? On Tuesday?
Yeah, I attended.
Yes. Oh, I got it now. So total internal reflection we had started. So total internal reflection, basically a very small portion of this is left because we have to do spherically refracting surfaces. So let's quickly cover this up. See, in this, whenever the ray of light enters from a denser to a rarer medium, whenever ray of light enters from a denser to a rarer medium, the light gets internally reflected if the angle of incidence is greater than the critical angle. And critical angle is which angle? Whenever the angle of refraction is 90 degrees. Fine. So, sine IC is equal to the ratio of the refractive indices. Now, one question we had done, this was an important question that we had done. One more important question, let's do based upon this only. I had told you, from total internal reflection, you get good questions. So this question basically says that this figure shows a cross section of light pipe made of glass fiber of a refractive index 1.68. Now the outer covering is there and inner covering is there. So outer covering is 1.44 and the denser part is 1.68. So what is the range of angle of incident rays with axis of pipe for which TIR occurs in the pipe? It means, look in the figure. This figure is already given to you. This is a part of question. This is not the part of answer. This is given to you. Let's say this is the inner pipe, that is the outer pipe. Now what will happen? The ray of light is incident over here, fine? And it gets refracted from air, it is coming. So this is actually air and pipe interface. I'll show you. The pipe starts from here. So now is it fine? I hope now you'll be able to understand. Look here. Ray of light is incident from air to this medium. So ray of light is getting into the glass. Definitely refraction will occur. It gets refracted at this point. Fine, it is getting refracted. So from air it entered. Now when it reaches here, somehow all the conditions of total internal reflection are satisfied. So if all the conditions are satisfied, then TIR will occur. It means the ray will get reflected here only. Angle of incidence is greater than the critical angle that is present. What do we have to calculate? We have to calculate angle of incidence here only. Angle of incidence. Before we calculate anything, sine IC. What is IC? What is this critical angle? What is this angle? The angle that is greater than critical angle. Let us find out this first, because without this we won't be able to solve anything. Fine. So let's apply simple Snell's law. I've told you in TIR nothing new is applied. The basic concepts are only used. So NDR, I've told you, refractive index of denser with respect to the rarer medium. That becomes ND by NR. So denser is given as 1.68, rarer is given as 1.44. And sine IC is what? 1 by NDR. So here sine IC will become 1 by NDR, means reciprocal of this, that is 1.44 by 1.68. This is sine IC. So when you solve this, your answer will be somewhat 0.86 sine IC. So this will be around 0.86. So if sine IC is sine, so this is one important data that we have, that sine IC is 0.86. We still do not have the actual angle of incidence from which the ray entered. So IC will be what? IC is sine inverse 0.86. Fine. Now for total internal reflection to occur, sine I, whatever is the angle of incidence, sine I Or let's say sin I dash, because your main sin I is this, what we have to calculate. This is the main I. Let's say this is I prime, so that you get you can differentiate between this angle of incidence and this angle of incidence. All right. So let's say this is sin I dash must be greater than sin IC. Now, if you look in this triangle that has been formed over here, yes. This triangle, if you look. So I1 means this angle is I1, no, which is greater than critical angle. Plus, this is the angle of refraction, R, and this 90 degree. All using angle sum property, you'll say all these three angles have 90 degree sum. So it means we can write, here we can write I prime, that is that angle which is greater than critical angle, plus angle of refraction from the air glass interface, plus the 90 degree that has been formed. This is equal to 180 degree. I prime plus R is equal to 90 degree. So angle of incidence will come out to be 90 minus R. Now it means sin I dash is greater than the critical angle. So what can we say? If sin I is greater than critical angle and sin I is sin 90 minus R. So this entire term is greater than critical angle. And what was critical angle? 0.86 only. And what is sin 90 minus theta? Can anyone answer? What is sin 90 minus theta? Trigonometric identity, sin 90 minus theta, cos theta. It is cos theta. So if this is sin 90 minus R, that will become cos R. Fine, this will become cos R is greater than 0.86. So if cos R is 0.86, then sin R will be what? Because we have to find out sin R only, no? C class. Why did we do all these steps? Because we want to find out this angle. This is unknown to us. And if we know angle of refraction somehow, then refractive index of air, we know refractive index of this material 1.68 also we know. We'll apply Snell's law, angle of incidence is clear. But we didn't have angle of refraction. So for angle of refraction, we used the total internal reflections concept that was given. Now we have sin R. And now using this, we can calculate sin I and value of angle of incidence. So now what do we have? Now we have cos R. Using cos R, we can say sin R is what? Under root 1 minus cos square R. Cos square R plus sin square R is equal to 1. That identity I hope you all must be knowing. So sin R is under root 1 minus cos square R. So sin R is under root 1 minus 0.86 square. Because this is cos R, no? So once you solve this, sin R will be greater than, or because greater than sign is also greater than or equal to 0.26. Now you have sin R's range, because also in the question also direct value is not asked to you. Range is given to you. Now if you will apply angle, I'll show you. Now if you apply Snell's law at this point, at this particular point, let's say some point, take it as P, N, Q, any point, let's say N point is this. So refractive index of the medium multiplied by sin I is equal to refractive index of the medium multiplied by whatever is the angle, that is sin R. This is how we use Snell's law. Or you can say sin I by sin R is equal to ND by NR. This also you can say, or you can use it like this also. 1 into sin I is equal to 1.68 into sin R, like this. So 1 into sin I is equal to 1.68 into sin R. Fine. So now sin R is also, so sin I will not exactly be equal. It will be greater than or equal to 1.68 into 0.26. So your sin I value will be greater than or equal to 0.436, somewhat this. So I will be equal to or greater than what? Sin inverse 0.436. So inverse trigonometric function you can use everywhere. Fine, like this. So I'll tell you the steps what we did. Later you can copy it down right now. A ray of light was incident here. It got refracted and it got totally internally reflected inside. we wanted to find this angle of incidence. Now, Snell's law we can apply because we have refractive index of this material, we have refractive index of this material. But for Snell's law, sine r is also required. So angle of refraction is unknown. So for the calculation of angle of refraction, we used this triangle. So I dash plus r, somehow we got the value of sine r. So now once we have the value of sine r, we calculated it using this triangle. Angle of, because critical angles condition also we know, critical angles formula we know. Using that we calculated I dash. Once we have I dash and we already know that this is 90 degree, using simple trigonometry we calculated r. Now sine r is there, sine I is there, both the refractive indices are there. Sine I simply it can be calculated. So note this down. Any queries if you have in between, just let me know. I'll explain that part. All have completed? Okay, all have completed, I think. See, now applications of total internal reflection are left. Some applications are there. Just have a look at the applications. It will come in a theoretical part. So definition will come, conditions will come, and applications will come. Numericals, we have done such types of numericals are only there. The other numerical also, which we did in the last class, where that square plate was there, same things were there, no? Same steps were repeated. So right now also in application part can come in your exam. So first application is mirage formation. So here what happens, see, atmospheric layers are there, right? Layers of atmosphere are there. And from the lower to the higher, the refractive index increases. From the very layer from the layer that is very close to Earth, it has a lesser refractive index than the layer compared at a greater depth. Fine, at a higher altitude, you can say. So refractive index gradually increases. If refractive index changes, speed of light will change at every step. So it can occur if the temperature is there, high temperature is there, it can occur that as suppose, let's say this is an object. So as the ray of light is coming from the object, I have told you in the first class, remember, objects are sources of light. It can be luminous, like directly from this light, or it can be non-luminous where light hits on the non-luminous object. Fine. Similarly, object means source of light. So rays are coming, getting refracted, getting refracted, getting refracted like this. It will keep on getting refracted. And so many layers are there in atmosphere. So when the light ray enters from denser to rarer, and somehow it exceeds the angle, critical angle. So which phenomena will occur? Total internal reflection. So when total internal reflection, let's say at this particular point, total internal reflection occurred. Reflection means what? Image formation will occur. Same thing. Whatever we have studied in reflection, this will occur over here. So we are able to see image like this. This is an actual example of an optical illusion. Here, what will happen? For example, if you are moving on road, sometimes what happened? The sky is from the sky, the rays of light come and it keeps on getting refracted. And on a very, very dry road, on a very sunny day, at a certain distance, now you'll observe water is there. You'll see water is there. But when you will come closer to it, you'll see nothing is there. The road is as dry. So what happened? Basically, it was the reflection of sky that you were able to observe. Or not even sky, you can take this example. You will be able to see the image of the tree on the road without the mirror. Because that is not an actual image of tree that has been formed, or not a tree has been kept within the ground. But because it's an optical illusion, so because of refraction, because of the refracted ray that is falling and the ray that is getting totally internally reflected. If it was not to be reflected, it would have gone straight away and no other cause would have appeared. Now, since it is getting reflected, reflection phenomena will occur. So this is one good example of TIR. One is brilliance of diamond. In case of brilliance of diamonds, what happens? Once the ray of light once this ray of light enters the diamond, because of the specific shape of diamond, what happens? It keeps on getting totally internally reflected. It's like the light gets trapped within this prism, within this diamond. So it keeps on getting reflected, then again it will reflect, then again it will reflect. So in diamond, now if you move the diamond shines. So that brilliance of diamond is because the light rays are actually getting totally internally reflected. And for your knowledge, you can remember that critical angle of a diamond is 27 degrees. This you can remember. This nobody will ask you, but whenever you're writing exam, if you make your points clear, it can be good for you. Then, yes, totally reflecting prism. So for prism, the critical angle is around 42 degrees. Now what happens? If a ray of light is there and I want the image to be reflected by 90 degrees, reflection can occur in any direction. Reflection is independent. No, reflection depends upon which conditions. The laws of reflection we have studied. But if I want to reflect it by 90 degree, I can use a prism. So what will happen? Rays will fall, then rays will go here after getting totally internally reflected at this point. So 90-degree image will be formed. Suppose I want to reflect it by 180 degree. These two are very important because they can be asked separately. The rest any cannot be asked separately. So here rays of light will come, rays of light will come. Totally internally reflected, totally internally reflected. Then again TIR occurs, here you get the image. So this is a right angle prism that you have 45 degree, 45 degree. It's just the plane in which you are allowing the object's rays to fall on it. When it was the perpendicular, you got it reflected by 90 degree. When it was the hypotenuse over here, it got reflected by 180 degree. So using just tilting the prism, you can reflect the light rays. So it is useful in reflecting the light rays with whatever suitable angle you have. Two examples are very common. This can be separately asked. That's why I'm saying this is important. And last is optical fiber. This is just the case that we have done right now. Right now, we have done that fiber, that wire was there. So optical fibers are those fibers that are used in computers. You must have heard of optical mouses, you must have heard of, or you must be having it in your desk along your desktops, which has light and a scroller is there. So that also has optical fiber. So that light that comes and mechanism, this is not into your detail in your syllabus, but you should remember that within these optical fibers also rays of light travel through totally internal reflection. They do not fall straight away, light rays. So that light, whenever this appears within the mouse, that is because of the optical fibers present. And why in optical fibers? Because of TIR. And this is same. How it can happen? We have done even a numerical on this. So you can relate it to this. So note down these examples. These are important. This is an important topic. As I've told you in the last class also, TIR is an important topic. Note down these in words. Even if you want, you can note it down. Wherever get stuck, let me know. I'll help you right now. Otherwise, make these figures. In the exam, write proper words, whatever I've told you. And even if you want, you refer to your books also for the application theoretical part. But this is enough. These are the TIS applications. So spherically refracting surfaces, now this is not lens right now. This is what? That circular part we had from which we constructed the mirror. Remember, we silvered it on one side and we obtained the mirror, and whichever side we silvered, accordingly the mirror was obtained. For example, if we silvered the bulged part, so we obtained a concave mirror. From here, the reflecting rays would have fallen. And if we silver from the inner hollow part, then reflection will occur from the outermost bulged part. That forms a convex mirror. Now, if I do not paint it, I just take a piece of glass, then what will happen? How the refraction will happen? What the formula will be obtained? First case, when we obtained the mirror, we had polished it and made one side opaque. Then only from one side reflection could occur. Now what is happening? Now I'm not polishing it, I'm not silvering it, simply I'm taking a piece of glass. So now what happens? This is what we have to deal with right now. So see, right now we are going to see a relation between refractive index between both the medium, that is the air you can say, or any medium outside, and the glass is a refractive index. Radius of curvature, object distance, image, since their relation. Now, their relation also, we are going to see it in two respects. One, if it occurs from rarer to denser, or if it occurs from denser to rarer. Fine, this is what we have to derive it. Now, let's say refraction from rarer to denser medium. So, fraction occurs from rarer to denser medium, no? So this is a piece of glass that I have. Fine. This refraction is occurring from rarer to denser medium. This is N1, this is N2. Fine. Now here object is there. Let's say object's rays are falling. This is not a mirror, so conditions and formulas will be different. So this is the incident ray. Fine. If we drop a normal, what I have told you for spherically refracting surfaces, if you have a sphere, always the normal will pass through the center of curvature. That's the way of drawing the normal. Even if you forget how to draw the perpendicular on a curved surface, join the line to the center of curvature. When you join that line to the center of curvature, this becomes the normal. Fine, this becomes the normal. And some things, and yes, now refraction will occur. And let's say here the image has been formed. Fine, this is the image that has been formed. One perpendicular I am dropping just for the derivation purpose, because this derivation comes in your exam. Lengthy derivation, it's there, but steps are simple. If you see, it's just practice one or twice, you'll be able to manage it. This angle, I'm saying alpha, random angle, no physical significance. This is also beta and this is gamma, just for derivation purpose. But angle between this and this is the angle of incidence, which has a physical significance, which we all know. Angle of incidence is the angle between normal and incident ray. And again, normal, and this is the refracted ray. So this becomes angle of refraction, angle of refraction, right? So incident ray, angle of incidence, refracted ray, and angle of refraction. So this part will become the radius of curvature. So let's say this is the pole. This is the pole, no? And this part will become image distance, and this part will become object distance. Now, if we apply Snell's law at this point, fine, let's say this point. Let's take this as M, because I have written it here M, no? And let's take this as M. This is M. So if we apply Snell's law at here, so N1 into sin I is equal to N2 into sin R. That's how we write. Again, if anyone is having any difficulties in application of Snell's law, please let me know. Fine. So now, whenever we have small angle approximation, so tan theta and sin theta are almost equal to theta. For example, small angle approximation we use for angles which are less than 15 degrees. So if I have sine 7 degree, no, the value of sine 7 degree will almost be 6.9, almost 7 degree. So instead of writing it as sine 7, I can write it as 7 also because answer is same. Similarly, if it is sine I, so I can write it as I. If it is sine R, I can write it as R. Now, it's the main formula of Snell's law. So it means instead of writing n1 into sine I can write it as n1 into I is equal to n2 into sine R. I can write it as R. Fine. Now look at this triangle. This is point N1. Now look at this triangle. Look at this triangle OMC. Fine. Look at this triangle OMC. Just have a look. This is the exterior angle. This is the interior angle. This is the interior angle. Exterior angle property of a triangle says that the exterior angle of a triangle is the sum of the two opposite angles. So angle of incidence will be equal to alpha plus gamma. Fine. If you see this, look at this triangle IMC. Gamma is now exterior. This is the triangle. This is exterior. So exterior angle is equal to R plus beta. Fine. So in triangle, I'm just writing down these things. Wherever you're not able to understand any point, please stop me there. Fine, because the derivation is lengthy, so it can happen you will forget whatever was your doubt. So in between, you can text me also, you can unmute yourself and interrupt as well. So in triangle OMC, I will be equal to alpha plus gamma. And in triangle IMC, what was outside? Gamma. Gamma is equal to R plus beta. So what is the value of R? R will be gamma minus B. Now we have I with us. Now we have R with us. So instead of I and this R, I am writing this term and this term. That is N1. Instead of I am writing alpha plus gamma. Do you get it? And here also N2 into gamma minus beta. See, the next derivation will be having almost the same steps. That's why I'm saying. Now see, if we have to find out value of tan alpha, tan beta, and tan gamma. Why? Because small angle approximation and all these angles will obviously be small. We'll get the values of alpha, beta, gamma. So see, if you look at this perpendicular, no, why did I drop this perpendicular? I dropped it only because N and point P are very close to each other. So I cannot use this curve, no, because this won't form any figure and the derivation will be stopped. The derivation will be stopped directly. Instead of using this, a point that is very closer to P, this I'm using. Now, after solving this Mn, I'll replace it with P. Because obviously, this curve OPM, this is not any figure. If I drop a perpendicular, this is a proper triangle. So tan alpha, if you see, this is Mn divided by On. Fine, Mn divided by On, if you look. In this triangle, if you see Mni, tan beta will be equal to Mn by Ni. Fine. For gamma also, if you see MNC, gamma will be equal to Mn by Nc. So tan's all value we have. So in triangle, tan alpha can be obtained from in triangle OMN. Alpha, which is equal to tan alpha. This is equal to Mn by On. Similarly, in triangle for beta, we have Mni. So tan beta, which is almost equal to beta, is equal to Mn divided by Ni. Now, this does not stop over here. We have one more quantity, that is gamma to be written. So gamma can be found from the triangle MNC. Tan gamma is approximately equal to gamma, which is equal to Mn by Nc. Fine. Tan gamma is approximately equal to gamma, which is equal to Mn by Nc. Fine. Now, alpha, beta, gamma, all the values we have, we just have to substitute it. So if we substitute the value, this will become N1. So Mn by On plus gamma was there. So it was equal to beta plus gamma, alpha plus gamma. So Mn by Nc is equal to N2. So that was gamma, that is Mn by Nc minus that is left, that is beta, beta, Mn by Ni. See, Mn gets cancelled from everywhere. But now we have to understand what is On. Acha, one more thing before this. Instead of writing N letter, I can use P letter now. On is approximately equal to OP. What did I say? Why did I use this N? I used this N so that I could form a triangle. Look here. Yes, look here. In this figure that is obtained, this curve part, that is P that is involved. Is this even a figure? Is this even a figure? No. But if I drop a perpendicular, as soon as I drop a perpendicular very close to P point, I obtain a triangle and the derivation is completed. Because using this, no, there cannot be any derivation that was possible using just this curve. Now I have obtained everything in terms of N. Now can I replace it? Instead of N, I can write P. Agreed? Because these are very close to each other. So that's why P is everywhere I'll write P. Because Cn is nothing but Cp is radius of curvature. Ni is nothing but Pi is the image distance. That's why. So On will be approximately equal to OP. And this is also equal to minus U, object distance, and negative sign conventions we always have to keep in mind. Similarly, NC will be equal to PC. This is almost equal, this is equal to radius of curvature. And Ni is left, Ni is approximately equal to Pi, which is image distance. Why these are positive? Because these are formed behind it. Remember the sign convention, they are formed along the direction of incident light. And this is against the direction of incident light. So this is negative. Same sign conventions which we were using for mirror. Sign conventions, we are not changing the sign conventions. Now we can put this. So instead of writing On and everything, I'll use this. So this becomes N1 by 1 by minus U plus 1 by R is equal to N2, 1 by R minus 1 by V. So multiply N into this, multiply here. That makes it N1 by minus U plus N1 by R is equal to N2 by R. Same, multiply N2 here minus N2 by V. So now we have more or less obtained. We just have to finalize it a little bit. Let's just arrange it. So that becomes N1 by minus U plus N2 by V is equal to N2 by R minus N1 by R. Or you can write it lastly, N1 by minus U plus N2 by V is equal to 1 by R. We can take common, N2 minus NR you can write. So this is the final formula. Questions are asked from this. Direct questions are asked from this. But derivation is also there. So derivation is not very lengthy though. Whenever you will start practicing it, so this will not be so difficult. But yes, next we have from denser to rarer, but that firstly write it down from here. Any doubts you have, let me know. T class. Now, when you have it, Sarah, your internet is fine now? I think you were having difficulties, no, in logging in and logging out too. So see, now same things. If it is from denser to rarer, this derivation you can try this by yourself also. Same thing. See, the glass part is now this. This is the glass part. Fine, this is the glass part. So here the object is there. Object will be there. Now, the normal that will be dropped, the normal that we'll drop will be from passing from the center of curvature. So this becomes center of curvature. This is again alpha, this was gamma, and the image that will be formed, this will be beta. This will be the image. Again, we'll drop a perpendicular, that is MN. This is gamma. This will be a perpendicular. Fine. Now, same steps you will repeat it. What will be the difference now? I see the angle of incidence is this. Right, the angle of incidence is this. Angle between the normal and the incident ray. And angle of refraction is this. Now, I plus alpha will be equal to this gamma exterior angle. And in this triangle, CMI, that is this triangle, R will be equal to gamma plus beta. So again, you have I, again, you have R. All the steps same steps you will repeat. Exact same steps you will repeat. Tan alpha, tan beta, all the same steps. But the final equation that you will observe, this will be different. This will be N2 by minus U plus N1 by V is equal to N1 minus N2 by R this time. Fine. And yes, in both the formula, no, you have to use proper sign convention. So use sign convention. If object distance is there, take it as minus U. Image is negative, take it as minus V. Like let's say 5 centimeters image is given and you know it has to be taken as negative. So don't write 5 because here it is V. Write minus 5. Fine. Object distance you think is minus 3. So write minus into minus 3. Use proper sign convention. Fine. So note this down and do try this derivation by yourself as well as an assignment also and share with me. So denser to rarer, same thing. And again, yes, this is now denser, this is rare. Okay, Samia, that is not a very less score though. But that depends upon what type of paper that you've got. If you're getting for a tough paper, if you're getting marks within this range, then that is fine. If you'll practice more, and yes, definitely you have to practice more for your further exams as well. But just send me your question paper, Samia. On WhatsApp, no. Do send me your question paper so that I can give you suggestions accordingly, no? That how much marks, whatever marks you're scoring according to the question paper. Fine, so just send me your question paper also on WhatsApp. You have my number already. So send it me over there. Otherwise, if a paper is a standardized paper, then this marks is fine for right now. all of you try to obtain your score within 50s only. Okay, if you have your scores within 15, then it's fine for the time being. If it's a normal easy level paper, then I think all of you should get between 56 to 65 marks. 55 to at least 60 minimum have the target. So yes, practice more, all of you, and as soon as you all get your scores now, just share it with me. Then only we'll be able to plan our revision classes accordingly. So it was very good, Samya, that you have shared it by yourself. All of you who have received the scores of half-yearly, midterms, whatever model tests were conducted, keep on sharing it. And yes, when you'll write it till here, just text me done in the chat column. I'll stop the class then. Okay. All those who have completed, you all can leave. Let's meet in the next class now. Okay, thank you so much, class.